That works, right? Oh my God, that's big. Okay. Yeah, welcome to my talk. Today we're going to talk about Bitcoin and a bunch of other things. And I gave the talk a fun title in the hope that that would attract people. It's, oops, I accidentally made a Bitcoin miner. And I hope I'm going to say this sentence today at some point. And you're going to be like, oh my God, he said the sentence. And that's going to be quite a moment. I really hope we're getting to that point. And yeah, I'm also going to explain how Bitcoin works. But I will start with something else. And that something else is friendship. So today I had a friend ask me, okay, Noel, how are you feeling about the talk? And he said, I said, yeah, I'm quite excited. I'm quite nervous. And he said, okay, Noel, I think it's going to be a really bad talk because it's your first talk, right? And it's like a stand-up comedian who does his first talk. And I think I agree with him. Like, maybe this talk is going to be a bit funny, like a bit stand-up comedian funny, because stand-up comedians have nothing to lose, right? Anyway, so with that friend, I would associate quite a bad friendship, perhaps, because that was kind of mean of him to say that, right? So I define friendship as some kind of measure of how good friendship is. So I would answer the question of how good friendship is. We're going to talk about all of these things with the simple answer that I would associate friendship with a number between 0 and 10. Because some friendships are good, some friendships are really bad, like with that friend perhaps. And 0 would be a really bad friendship, 10 would be a really, really good friendship. And I know some of you are mathematicians in here, so this is a way to formalize that. I associate a friendship score with a number between 0 and 10 with 2 digits of precision, right? Because I don't want like real numbers. I don't want to bubble with that. I want to have friendship scores like 5.63 with Justus, for example. So I implemented this, and because I wanted friends to have the option to find out what their friendship score with me is, right? So, open website, Noel. I have this terminal, which hopefully you can see, which doesn't load. Oh, because you can't see it, because I'm having a PowerPoint open. That's fun, at least. Can I? Perfect. Does that work now? Yes. Okay, so I have this terminal, which is a website. And on this terminal, I can run commands. I can run commands like Fibo, and it will tell you all the Fibonacci numbers. I can say things like, okay, is prime 8? And it will tell you if 8 is a prime. But I can also say things like f, which calculates a friendship score with someone. And I could say f Justus. And it tells you, okay, friendship score of Justus 9.68, which is pretty good. Like on the friendship scala, that's pretty high. Because Justus is a good friend of mine, and you can put any name into this, actually. So let me just go back to the presentation. If you want, you can scan one of these QR codes and find out what your friendship score with me is. Like, maybe you have a really good one. Maybe you don't. You can try it out, and it will open like a form. It's not the terminal per se, but it's like a little form where you can type in your name, then you click run, and then it tells you your friendship score. Does it work? I need a thumbs up. Great. So what is your friendship score with me?
9.71.
Wow, that's suspiciously high. What is your friendship score?
8.7.
Wow. Okay. So we got a good friendship score. Has anyone got a really bad friendship score with me? Out of curiosity, what did you get?
3.5.
Oh, yeah. Well, to be honest, I don't really know you that much. So, yeah. The obvious question you may ask now is, how does it work? Like, how do I calculate friendship scores? And why are they kind of accurate? Like, I think this went quite well. I expected someone to have like 10 who I don't know, because that could happen. So let's figure this out together, how I made this. I have 3 conditions that I want to really get with this. I want anybody to type in their name, and if I type in F Justus, for example, because Justus is a great friend of mine, I want a high number. I also want, maybe don't want, a list of friends in my code, because the code from my website is actually public, and anybody can see it, and I really, really want to avoid the situation where there's like a list of friends I have online. Like, that would kind of be awkward. Also, it would kind of invade my privacy and maybe also theirs. Like, that's not a good idea per se. And thirdly, I want anybody to type in their name and get back a score, just like you did, because that's fun. And also, I want that score to kind of make sense, but perhaps it could also be a high score. Like, for example, one of you could have randomly gotten a high number, like 9, and that would have been good for me, because otherwise you could just run like all the 10,000 most likely names in English, and then just get a list of friends back for me, right? So we need some kind of false names that are also high, because I just want my friends to have high scores. So let's approach this problem kind of in a more mathematical way. I have an alphabet, which names are made of, and this alphabet is made of, let's say, the Latin alphabet, to simplify things right now, because we can associate Latin alphabet characters with numbers quite easily. And we include capital letters as well, but in truth, we can just lowercase the name, because it shouldn't really matter if I type in Justus with a capital J or not. I think that's kind of the same vibe. So I want to have a function that maps a word of this language of basically any length, could be a very long name, to a friendship score, which is a number between 0 and 10, right? So how do I do that? That's a difficult question, right? Does anyone have an idea how to do that? Yes?
Define certain values, and then define an analytic structure and interpolate.
Okay, so I want a very bad name and a very good name and interpolate between them? Or what do you say?
We pick them up so many points so that we somehow basically cover this sample space of sigma plus.
Yeah.
Since we're not usually considering extremely long names, so it should be actually somehow kind of tractably finite, and then we can then try to put some interpolation.
Okay, so what you want to do is you want to have a map from the space, and then do some function that interpolates between known values, because we used to have a high name, right? So that would have a high name, and then interpolate between them all, kind of smoothly. That would work. Unfortunately, that kind of relies on that being finite. You could make it work with infinite values, perhaps, but a very simple way of doing that would perhaps be something like this. This is just a sum. I could just sum over all of the characters in the name. And, well, to sum over characters, I first need to convert characters into numbers. So I could use something like the ASCII table, which already is like a map from characters to numbers, right? So I could say, okay, Justus, that's a capital J, that's 74, and so on and so on and so on. I sum all of those. And then I take it mod 11, and that will give me a number between 0 and 11. Or rather, actually, 11 is excluded, because 11 mod 11 would be 0. So that would give me a number like 10, or maybe 7. And you can make it work to give numbers with decimal points. You could do the sum and then mod 1001 and divide it by 100 or something. That would work, but it's quite hard to make this function work so that Justus gives me a high score. And also, like, this doesn't really respect order. Like, I could say Justus has the same score as Jutsu, because the sum doesn't really care about order. So I could have different factors, but I could make it difficult. Yes?
When on add a position of encoding just language transformers, so basically the first one gets a higher small value and the last one gets higher.
I could transform them in a way with constants in front and make positional encoding. But that would make things difficult, and honestly, I solved this in a very complicated manner, and to understand that manner, I want to first look a little bit about hash functions. And hash functions are functions that map a value of arbitrary size into a value of fixed size, right? So, for example, I could have a hash function that maps all of the names into a number between 0 and 10 with a friendship score. That's a hash function, right? It's not a very good hash function by some measures. We'll look at that later. But it's a hash function. And to understand why hash functions are perhaps useful and why it was quite easy for me to implement this, we're going to take a quick look at Bitcoin. Woo! Yay! Okay. So, Bitcoin is a digital currency. Bitcoin is kind of a first digital currency, actually. It was invented in 2008. It was published in a paper called, what is it called? Bitcoin a peer-to-peer electronic cash system. And it was published by a guy called Satoshi Nakamoto. It's probably a pseudonym. There exists a professor with the name Satoshi Nakamoto, but we're pretty sure that it's not the guy actually publishing the paper. So it's probably published by some random person. Maybe it was like some organization. There's a lot of conspiracy theory about who actually published it. But we have this paper, which outlines how Bitcoin works. And it's not too long, actually. It's 40 pages or something. You can read it, and it's quite readable. And I'm just going to summarize it now. And I think nowadays, if you mention Bitcoin, it gets associated with a lot of things, mainly things like gambling, Bitcoin mining, whatever that is, and things like crypto bros and it being decentralized and cool and hip. And let's explore why that is. So I'm going to give you a little bit of motivation, how Bitcoin works, a little bit of a summary. So I'm going to have 3 people that want to make transactions with each other. I have Ben, Alex, and Colin, which each have a very handsome face, I might say. And these 3 people, they want to make transactions with each other, and they don't want to use cash, because cash, that's so like 20th century. So they want to use a digital currency. So the easy option might be a ledger, to introduce some kind of list of statements that tracks how much everyone paid to everyone else. So for example, I could have the statements, Alex paid Ben 10 friendship coins, then Colin paid someone else. And if you keep track of the sums of these ledgers, you could keep track of how many friendship coins, or whatever we want to call this currency, each person has. So at the end of this transaction list, for example, Alex lost 55 friendship coins, Ben got 45, and Colin got 100. And you notice this sum of these, it stays constant, right? Because no money is lost, no money is somehow invented. And that might be a problem for now, but we could assume that everybody from the start has a certain amount of coins or something. That will work. And also, it doesn't really prevent anyone from going negative. Like right now, Colin might be a little bit angry at Ben and Alex because they owe him money, perhaps. Or do they owe the system money? It's kind of complicated, right? So this system has some imperfections. And I think actually the main imperfection of this system is that this ledger, this has to be agreed upon, right? This ledger has to exist at some point, and everyone has to write down the payments they make. But it has to exist somewhere in maybe digital, maybe physical form, and everybody needs to be able to write to that ledger, right? But Alex could just write, okay, Colin gives Alex 1,000 coins, and then Colin would have less money, and Alex would just win money, and that would be bad. So we're going to introduce our first concept, which is to sign transactions. And this is done using public key cryptography. Actually, behind the scenes of Bitcoin, it's done using elliptic curves. But I don't want to get too much into that. But basically, we have 2 keys, a public key and a private key. And the public key can be used to check a signature made with a private key. So for example, the statement, Alex paid Ben 10 friendship coins, could be signed by the person making that payment, so Alex, with his signature. And that signature is then kind of representative of him actually doing that thing. And we can check that using the public key. And I don't want to get too much into that, how this actually works. This could also be done with something like RSA. It turns out RSA would actually maybe be quicker, but let's not dive too much how this works. So let's go back into our transactions, which now have these awesome little signatures at the end. So we're actually sure that Alex made this payment to Ben, for example, because he signed it with his signature. And you notice these signatures are actually different for like the same people. So Ben paid Colin and Alex, but the signature is actually different. So the signature actually depends on the thing itself, because otherwise you could just copy the signature of Ben. So the signature is complicated, and it makes sure that Ben actually paid that. Okay. But this is not where the magic of Bitcoin begins. It's actually if you group these statements, these transactions, into something called a block. And this block can then be used to have some fun. And we can add something else to that block. We can add some random data. And we can also add a little bit of hashing at the top. And what this does is it makes a block. And now we have a very big block. It could include up to, let's say, 2,000 transactions. Let's say that block is the size of a megabyte encoded. And this entire block we can now store. And this block contains a ledger, so we can see who has how much money at the end. And this random data is just at the bottom. And what we can now do is hash the block. And if we hash that block, it gives us some hash value. We use a hash function again. And it gives us some hash of a block. We could see up there, there's the hash of a previous block. So that's the hash of the block before. But let's first understand this hash thing here. Because this hash function actually in Bitcoin, it's not like the hash function we looked at at the beginning, which was just a sum and then mod something. It's a cryptographic hash function. And cryptographic hash functions are actually quite a bit more useful than my hash function. So a cryptographic hash function has, I'd say, 4 kind of key attributes. And we'll go into them in detail a little bit later. But let's first look at the first 2. The first is that the output appears random. So if in a cryptographic hash function you input any amount of data, you get something else. And if you modify that data, the hash changes a little bit, but you don't know, actually not just a little bit, actually a huge bit, and you don't really know how that hash will change. And it looks kind of random, and we really want that to look random because that enables the second thing, which is finding an input producing a given output is infeasible, given that the input data is kind of random. That means that the function is actually one way, which is a really interesting concept mathematically, which means that if we input any data into a hash function, let's say the entire script of a B movie, then we get a hash, but it's really hard to get any other input data to produce the same hash. And we call this thing, when we find 2 different inputs which produce the same hash, a hash collision. And we really want to avoid these hash collisions because hashes will be really useful in like a minute. Okay, so these other two properties, let's look at them later. But these 2 are really important. And the main thing to take away here is that hash functions are one way. And you can only transform data in one direction, but it's really hard to find data that produces a given hash. Okay, so let's hash our block. And I hashed it for you. And I also included some random data here. I represent data by 0s and 1s because mostly everything can really be encoded by 0s and 1s. But it could be something like a sentence. It could be anything. It's just random data here. And at the end, I have 256 0s and 1s because that's the output of the specific hash function that Bitcoin uses. It uses SHA-256. We'll look at that in a minute, what that is. And now my goal is to find some random data to change and to do anything with it and look through loads of different random data so that that hash begins with 20 zeros at the beginning. So I'm going to look through a bunch of values. And actually, there's no quicker way than just looking through random values and finding one. And woo, wow, we found one. So we found one which produces even more than 20 zeros at the beginning, right? So this is now a mined coin, we call. And let's just accept that fact. So we have a block whose hash begins with at least 20 zeros. That's good. Now what we can do is we can put a second block next to it, and let's say that block includes another 2,000 transactions or so. And if you notice, the hash of the previous block is now in the next block. So these are kind of linked now, and we can do that for many more blocks. And we can have thousands of blocks which are all linked by each other by the previous hash. And this forms something called a blockchain, which is kind of a nice one. Kind of a nice word, I think. It's a very beautiful word because it's so visual, you know? And the really cool aspect of this blockchain is if you change anything except maybe the last block in the blockchain. For example, if I were to change this Alex to Ben, then the entire blockchain after that would fail because the hashes rely on each other. So if I change the Alex to Ben here, for example, the hash of this would be different, and wouldn't be 20 zeros. And okay, that's cool. We now have a blockchain. And actually, once like the final block is hashed, it's really hard to like manipulate data here and have it not be visible at the end. But how can we use that now to make something which helps us make transactions? So we have a blockchain. Okay. So let's look at the Bitcoin network. Let's go back to Ben, Alex, and Colin, who all have very handsome faces. And let's see how they make payments now using this blockchain. So Alex, for example, could say, okay, guys, I'm paying 10 friendship coins to Ben. And we know that Alex is saying this because Alex signed this message, right? So we know Alex said this, and he sends this to everyone in the network, to Colin and Ben. Ben and Colin receive this, and every one of these keeps their own list of transactions that happen. So every one of these keeps their own ledger. So everyone knows how much money everyone else has, and everyone in the Bitcoin network keeps a ledger. But there's also other people in the network called miners. And these miners, they also listen to those statements. And yeah, the miners, they produce Bitcoin, right? So they listen to this, and they are really thirsty for Bitcoin. So they want to get this, and they want to turn that new payment that just got made into a new block to add to their blockchains. Because each one of those miners has a blockchain. In fact, actually, everyone has a copy of a blockchain at home, basically. And then the first one of these miners to produce a block that fits into the blockchain, meaning a block that, if hashed with random data at the end, produces a string with 20 digits of zeros at the beginning, they make a new block. And they can now say, oh my God, guys, I just found a new block. And my block starts with 20 zeros, and probably no one else found this before me, because it's really, really hard to find this block, right? Like 20 zeros at the beginning, that's pretty unlikely. We know the hash function it's meant to be random, right? So the probability of that happening is 1 divided by 2 to the 20, I think, which is like 1 in a million, right? So that miner probably went through like a million blocks, a million random datas, and tried to encode that and add it to the blockchain. Okay, so that miner is now happy. And he's really happy because the miner gets the reward for it. Because this is Bitcoin, and we get rewards if we make a block and we add it to the blockchain. Because this miner will add a statement at the end of that block saying, okay, and I get a reward, something like 3.25 Bitcoin, for example. Okay, so that miner is now happy, and each one of these miners has their own copy of a blockchain, and these blockchains are all like of different lengths because everyone's working on their own blockchain. But they make sense, right? Like the hash of this at the very end still produces a valid blockchain. This one produces a valid blockchain. And you can see that different lengths have a different amount of transactions. So when new transactions come in, new blocks get added to the blockchain. But how do we agree on which blockchain now is the right one? And Bitcoin has a very simple solution to this. And this is kind of where the magic of Bitcoin lies. And that is to just accept whichever blockchain is the longest. Because what's associated with those blockchains is a lot of work, right? Like this guy, this miner, who's clearly having Bitcoins, because 2 Bitcoin signs there, he has the longest chain, and he's put the most work into it, right? Like a lot of work. Like each one of those took a lot of work. So he's got proof that he does some work. And when a new miner joins the network, he could just say, okay, let me just take over, let me just copy the longest blockchain we have so far, and let me work on that. And now it's really, 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 really hard to include like a fake block of yours. Because, for example, let's talk about the problem we had before, that Alex could just write a new message for someone. If Alex now wants to fake a message, he needs to put that message into a new block, and then mine this block for him, right, to add it to the new network. But what does he have to do then? He needs to mine that block. So maybe he's lucky. Maybe he's quicker than all the other miners. And he has the longest blockchain now. So he just added a block with him in it saying, like, he got 2,000 Bitcoin. But what now? What happens now is all the other miners, they might catch up to him. They maybe produce other blocks and longer blockchains with other statements in them, right? So at some point, what might happen is that Alex isn't like the guy with the longest blockchain anymore, at which point he will get overrun. Because, this is a quite important principle of Bitcoin, there are a lot of miners, right? And if more than 50% of the people have a long blockchain, then we could say that it's some kind of agreement. And this idea of agreement by majority is kind of what makes Bitcoin work. So if we could define the longest blockchain to be the blockchain that like 50% of the people have right now at home. And they keep publishing those blockchains to everyone else. So we know what the longest blockchain so far is. And for Alex to commit fraud, it's really, really hard because he needs to beat 50% of miners. He could do that if, say, you're the NSA or something, and you control 50% of all the miner Bitcoins, of the Bitcoin miners, then you could fake payments, right? But the assumption here is that enough miners exist that probably the NSA can't do that. And who knows, maybe the NSA can, but probably there's enough miners on the Bitcoin network to facilitate this. Because miners make money, right? Because every time they mine a block, they get a reward. In fact, this reward, it's very funny. It gets different. Like at the beginning of Bitcoin back in like 2009, the reward was very high. It was like 1,000 Bitcoin that you get per block mined. But then every approximately 4 years, the Bitcoin reward it halves, which means that at the beginning it was 1,000, then it was like 500, and now it's 3.25 Bitcoin. And in another 4 years, because it just halved this year, it'll be like 1 point something Bitcoin. So it always gets less, and as I assume most of you mathematicians know, if you always halve it and if you sum it up, that's a finite limit that you reach at some point. And the idea behind that is that there's only a finite amount of Bitcoin in the world. Like the maximum is only, I think, 21 million. And you can't really reach that ever, because in the end, the halving and halving and halving and halving and halving and halving will mean that no more Bitcoin enters the system. And the idea behind that is that at some point there's enough Bitcoin, right? At some point the system will just work. Of course, miners might not have incentive anymore, but that's pretty far into the future, so let's not worry about that right now, and Bitcoin will work. So there's a few issues with the system, and the main one is that this Bitcoin mining is really expensive. So this arbitrary problem of finding like the first 20 digits of a hash to be 0, that's a really, really hard problem to solve, and it's really computational intensive, right? And there's a lot of miners in the world doing it right now. And it's perhaps like the algorithm that gets run the most, because there's a lot of computers on right now just running the hashing function, trying to find a block that starts with 20 zeros, trying to find a hash. And you could argue that that wastes a lot of power. Like, we could solve other problems with that compute power. And people have suggested like different hash functions. There's theoretically the option to use like another sort of problem. Like you could replace with finding 20 zeros for a hash with something like solving a Sudoku, because that's also a problem that's really hard to solve, but it's quite easy to verify. Like computing the hash of a block and actually checking if someone was successful is quite easy. Like it's a hard problem to do, but once you found a block that random data which means that the block starts with 20 zeros at the end, you could quite easily verify that. And with Sudoku, it would kind of be similar, right? You could solve a Sudoku, or maybe you could solve some NP problem it's very easy to check. But right now, this is how Bitcoin works. And Bitcoin only gets reworked every so often because Bitcoin accepts changes to the system, but only by majority. So there's always big dispute between all the people that use Bitcoin, and they implement new protocols every so often. They change how many zeros you need to make it so that every 10 minutes or so a block is created. They tune parameters, and there's always a lot of fights in the Bitcoin community, actually. So, for example, 5 years ago, there was a really big fight over something principle, which is this 10-minute limit, which is the idea that a block can only be created every 10 minutes. And some people just said, okay, we won't get a majority with this. Let's just make our own cryptocurrency, and let's name it Bitcoin Cash. And now that's the third biggest cryptocurrency in the world, which It's basically just Bitcoin, but with a few changes. Like it has faster block creation, it has more storage per block, and so on. So Bitcoin was created in 2008, so it has some improvements. And so far, there's been a lot of working on new cryptocurrencies that like improve things. Like I think the most famous one is ETH, like Ethereum, which says the initials with this university. It's one that has a new block, I think, every 2.3 seconds or something. So it's a lot quicker and can process a lot more payments. Because this is a huge issue, right? Like a new block every 10 minutes. That means 2,000 payments can be done per 10 minutes only. That means if I want to make a transaction, I need to wait for there to be a slot, right? Or actually, nowadays, we need to pay miners. So we include like a little transaction fee at the bottom of our payment, saying like, hey, if you include this payment in your new block, then I'll give you like a little bit of Bitcoin, which is nice, but it means that we have transaction fees in Bitcoin now, but that makes things more complicated. Okay, Bitcoin. Now we're Bitcoin experts. I'm sure you have a lot of questions, but that was a little introduction to Bitcoin. So let's get back to this, which is my code for computing the friendship score. So let's understand this code. Let's look at the main part, which is this function random friend score. By the way, I'm not assuming that you understand this code, like the syntax, but I think you can roughly see what it does. Let's zoom into random friend score. It does two things. The first thing is that it computes the SHA-256 hash of friend name, because it's really easy in a language like JavaScript to run SHA-256, which is the hash algorithm used by Bitcoin, by the way, because I can just call it, and that way I don't have to like program any fancy new hash function that's designed by me. And then at the end, I just take the first two like bytes out of that hash, and I turn it into a score between 0 and 10, and that's my friendship score. And to verify that actually Justus gets a high score, I added this string, which is called a nonce. So if you type in F Justus, it doesn't actually hash the name Justus. It hashes the name Justus and adds like a little bit of characters, a nonce at the end. It adds the characters P, X, X, TH, F, NO, N, and so on. And what that does is that I tried loads of different nonces, and I found a nonce for which Justus gets a really high score. And I found a nonce for which another friend of mine got a really high score. And I actually found this nonce, which gives basically most of my friends good scores, at least sufficiently good scores. I can't control them exactly, because that's, again, a really hard problem. But by finding this nonce, I don't know if you noticed, but I kind of wrote a Bitcoin miner. This is the moment where you go like, wow, oh my God, you wrote a Bitcoin miner, okay? And this is kind of crazy to me. Like, I wrote this before I knew anything about Bitcoin and how hashing works. I just found this online, the hashing function, and then I wrote some code, some dirty code, to generate this nonce, which basically just went through a lot of nonces. And that was essentially Bitcoin miner, right? Because a Bitcoin miner would do nothing else. It just takes random data in. It tries it against the data plus something else, in my case, a friendship name, in Bitcoin's case, a block, and then I want a high score. I want Justus to have a really high score, right? So yeah, that's how I accidentally made a Bitcoin miner. But we still have time, so we can talk about cryptographic hash functions for a minute. But before we do that, I think there may be some questions about Bitcoin. Is that true? Anything to clear up? Yes?
So as I understand it, there's like one main blockchain
Yep.
that everybody kind of shares.
Yep.
You said one block is something like 1 megabyte.
Yep.
And you said there could be some, so where is that stored? Is that on every computer?
Yeah. It's 1 megabyte is specifically chosen to be quite small. So the question was if the megabytes isn't, where is that actually stored? Like, where are the blocks stored? And the answer is that it's basically stored on everyone's devices, right? Like, every person in the Bitcoin network just keeps them at home and sends them every so often to the whole wide world, to everyone else, basically. And everyone who joins the network at some point or leaves it again just picks up where everyone else left off. So it's stored in every device, yes. And 1 megabyte might seem large, but the Bitcoin, like the whole blockchain right now, it's not actually that big. Like it's only a few, I think, terabytes now, which may sound large, but for like Bitcoin miners, that's absolutely fine.
But like my computer, I don't think it has more than like 1 terabyte.
Yeah.
But how is it stored on my computer?
Yeah. So the good thing is we have miners, and they store that for us. And when we make a payment, we just tell all the miners what we have. And the assumption kind of is that there's enough miners who keep keep track of things. But let's say in a scenario where all the computers of the whole wide world shut off, then the Bitcoin, it's lost, right? Like if no one stored it at least. So yeah, we just send it off to some miners. Because we don't actually need to know it, right? We just tell them. Yeah.
So what happens if I make a transaction with a miner that has a shorter that ends up having a shorter blockchain than others? Does it get lost?
Yeah, so your question was that if you send a message and perhaps some miners have different lengths of blockchains right now, does it get lost, that payment, because it gets picked up by someone with a small blockchain? And everyone works on all payments, basically. Like all the miners with all different lengths of blockchains, actually all blockchains are kind of similar in length because they discard, like, if a blockchain is really, really short in comparison to others, then it doesn't make sense to work on it anymore. Then you can basically trust it because the chance of it being, like, fraudulent is very, very low. Like, if it's more than 10 blocks longer, then we just copy that one. So, yeah. Also miners with smaller blockchains work on your payment, and only those with like the longest blockchain will get approved in the end. But it only matters that it's like included in the longest one, right? So sometimes it happens that miners find blocks that don't get accepted in the end, and then they make nothing. And that's a problem, right? So they try to avoid that situation. So they try to always have also a mostly quite long blockchain. So, some try to like snag coins off by having a shorter blockchain, but basically all of them have the longest one, yeah.
My question is more regarding the process of mining. Why do miners specifically use graphics cards for their mining rigs?
Yeah, they use graphics cards because graphics cards are very quick. So the question was why miners use graphics cards, like a lot of them, right? Like you could see that when crypto was booming, when there was a big crypto hype, that graphics cards were really expensive suddenly because a lot of people bought graphics cards. And then actually, by the way, this year was one of the coin halvings, like reward halvings. So this year, you could see like when the coin reward was halved, that graphics cards were suddenly a bit cheaper again because people bought less of them. It's quite funny to see, and it's because graphics cards are very quick processors, basically. Like, graphics cards have a lot of parallel computing units. Like, they can do thousands of operations at the same time, which is important because the SHA-256 algorithm, it runs on a single core, so it makes sense to have multiple cores in parallel. But actually, the best Bitcoin miners, and I think it's kind of a necessity nowadays, they have like custom cards, custom chips that specifically only run that function. Like they're extremely quick. It's like hardware accelerated, and it just does the hardware version of SHA-256 over and over and over, much quicker than any graphics card. Yeah.
The incentive is half every 4 years or so.
Yeah.
Isn't there a point in the future where it doesn't make any sense to farm or mine more Bitcoin if the price doesn't correlate with the halving?
Yep.
So we'll get less secure then.
Less secure in the sense of what? Because, of course, there are a lot of miners that are just interested in keeping Bitcoin mining running as well. Like, for example, a lot of universities actually have Bitcoin mining centers just trying to keep up the system. It's probable that also, like, some governments have mining centers. Like, probably America has some big institution. So there will still be some miners online. But, yeah, over time, mining gets less profitable. Yep. So Bitcoin is not here forever, but the assumption is that in the time we will solve this problem by some measure. And that's possible, right? Because we can agree on something else, perhaps, in a few years. Maybe there's another coin. Maybe you can do something else. And as long as 50% take over that change, which would make sense at that point, it's fine. Yep.
I'm not sure if I understood right, but when you buy to recreate this transaction somehow?
Well, they include your transaction in their block, in a new block they're making. So they collect like 2,000 transactions until they fill a block, and then they work on that random data at the end of the block. And they just modify that to make the hash work. Right. Okay, I think we have a little bit more time, like 4 minutes. If someone has more questions, if not, then we can talk about cryptographic hash functions for a minute, which is amazing because that's really fun. So I talked about the first two, but cryptographic hash functions actually have a lot more kind of fun properties, and I think they're quite unbelievable that they exist, and I want to highlight 3 of them. And that's a funny transition. The most amazing fact about cryptographic hash functions for me is that they are public. Like, I can see the code, right? I can go on Wikipedia, and I can see how it's written. And this is the code. And you see a lot of numbers. And it was actually written by people who we pretty much know to be in contact with the NSA. So maybe this is scary, you know? Maybe these constants are encoding some things quite scary. And then it does some stuff. It does some calculations. You see it does like a lot of write, rotate, XOR. Like it does modulo at the end as well. And it's basically a big fumble of different operations that they do after each other. And the assumption is that after like 80 iterations of this, it's really hard to make an inverse of this function. And so far, nobody has found an inverse. Like if you found a way to produce a hash collision, so to, for example, find 2 inputs which produce the same hash, then you're practically rich. Like that means you can solve SHA-256, which is not only used in Bitcoin. It is used in Bitcoin, but it's used everywhere on the internet, kind of. It's like used in HTTPS to verify that this Wikipedia website is working right now. It's used in bank transactions. It's really useful. And there are more hash functions. SHA-256 stands for Secure Hash Algorithm, with 256 meaning that the output is 256 bits. But there's also new hash functions. You may have heard of like Shor's algorithm, which is an algorithm that could run on quantum computers. That could probably solve if quantum computers work with an okay time complexity. So maybe that would break SHA-256. So there's actually new hash algorithms, SHA-3 and stuff, which are quantum resistant. But I think it's so surprising that it's like public, right? I think that makes so little sense, but it still exists. So that's good. Another thing is that so far, there hasn't been like found any collision, and I know we only have 1 minute, but I want to say this. Like it's crazy, right? Like you could be the guy to find 2 inputs which produce the same hash. You could be the lucky guy. You could just try it out on the website right now, but it probably won't happen. But you could be the guy, and no one has found one. Like that's crazy. It's very unlikely that it will happen, but why not? And the last one is they're super sensitive. So if I put like the script of B movie into it, or like if I put a picture that's like megabytes in size into a hash function and change just 1 pixel by one point, then the entire hash output will be very different. Yep. So that's fun stuff about hash functions, and that was my talk about Bitcoin, and that was my my little path into Bitcoin. Thank you very much for coming.